When you and a friend point up at a rainbow after a storm, you aren't looking at the same physical object. A rainbow is an optical event rather than a solid thing, and no two people ever see the exact same one. The arc's position depends entirely on where your eyes are located. Because each person captures light from a different set of raindrops, your left eye actually sees a slightly different rainbow than your right eye. Notice the colors themselves. You will never see brown, black, or gray in the arc. Those aren't pure colors, but rather mixtures or the absence of light. A rainbow is a frequency map, displaying only the fundamental tones of the electromagnetic spectrum. This transition is striking. A storm is a chaotic system of tumbling water and scattered white sunlight. Yet nature organizes that chaos into a structured light show governed by strict geometry. To understand how the atmosphere builds this macro-scale illusion, we have to look at the microscopic physics occurring inside a single drop of water. As rain falls, surface tension pulls the smallest droplets into nearly perfect spheres of liquid glass. This cross-section shows what happens when a beam of sunlight hits the water surface. As the light moves from the air into the denser water, it slows down and bends at an angle. This is called refraction. Because white light is a mixture of all colors and different wavelengths bend at slightly different angles, the beam separates. This dispersion turns the single beam into a fanned-out spectrum of color inside the drop. When this light hits the back of the drop, it doesn't pass through. Most of the light bounces off the back surface, which acts like a curved mirror. This internal reflection directs the light back toward the front of the drop. As the light exits the drop and speeds up in the air, it bends a second time. This final refraction amplifies the separation of the colors, sending a wide spray of light toward your eyes. This optical chain relies on the drop being spherical. If a raindrop gets too large, air resistance flattens it like a hamburger bun. This physical distortion shifts the exit angles, causing the colors to blur or the arc to lose its shape. A single spherical drop acts as a miniature lens. To create the giant arc in the sky, billions of these drops must align with the specific perspective of the person watching. To see the result of this alignment, you must stand with your back to the sun, facing the anti-solar point, the spot exactly opposite the sun's position. Out of billions of falling drops, you only see the color from those positioned at a specific mathematical constant. For a primary rainbow, light exits the raindrops at an angle of approximately 42 degrees relative to the incoming sunlight. Sometimes, light reflects twice inside the drop before exiting. This creates a secondary rainbow, a fainter, wider arc with its color order completely reversed. Between these two arcs, the sky often looks darker. This is Alexander's band. It occurs because the raindrops in this specific area are reflecting light away from your eyes rather than toward them. A rainbow is entirely dependent on geometry. It is a temporary alignment connecting the sun, the floating water lenses, and your exact spatial coordinates. Because the rainbow depends on these environmental factors, changing the atmosphere or the medium alters the visual output. Fog droplets are much smaller than raindrops, which causes light to diffract rather than just refract. This washes out the colors into a white fog bow. During sunset, the atmosphere filters out blue and violet light, leaving only red and orange to form a monochrome red rainbow. The internal reflection that directs light back to your eyes also changes its physical properties. The waves exit the drop, vibrating in a single direction, parallel to the arc, a state called polarization. Because polarized sunglasses are designed to block light vibrating at specific angles, tilting your head while wearing them can make the entire rainbow disappear. On Saturn's moon Titan, it rains liquid methane. Because liquid methane has a different refractive index than water, the light would exit at a wider angle. A methane bow would appear much larger in the sky than a rainbow on Earth. The appearance of a rainbow acts as a visual report card, providing data on the chemical and physical makeup of the atmosphere it forms in. The bow shape we see from the ground is an illusion caused by the Earth's horizon, which blocks the bottom half of the geometry. From a high-altitude aircraft or drone, the horizon falls away. Without the ground to interrupt the light, the arc connects into its true form, a full 360-degree glowing ring. This ring is a sphere of light centered exactly around your position in the sky. A rainbow is the visual proof of the laws of physics. It is a balanced display that requires the sun, the rain, and your perspective to align perfectly in order to exist.